That's crazy. That is way outside Triplicate's comfort zone. Not a lot of channel content getting made at the minute. Hi there, and welcome back to Triplicate and what is part 5 of our radical synth development, which unfortunately still lacks a name. Anybody with any ideas, please feel free to leave them in the comments. And so far, well, we've decided our synthesizer is not going to have conventional synthesizer, oscillator, envelope, filter, etc. architecture. We've decided it's not going to have a piano style black and white keyboard. We've decided it definitely isn't going to have MIDI, and we've decided we want it to have a bit of attitude. And last time we were looking at how we're actually going to make a sound without a conventional oscillator envelope setup, and by way of a bit of fun we developed an oscillator using a neon. And here it is. We'll just fire it up one last time. There it goes. And we will just zoom in here. And here we are zoomed in, and you can see our little neon blinking. And then we try to build a software model of this using a very crude model for the neon, just using if the voltage is greater than something turn on, and if the voltage is less than something turn off. And we found this didn't work for the usual reasons of doing things with sharp transitions in digital sound. So we now need to find something other way of modelling some kind of a system with two semi-stable states. And to do that, I thought Triplicate might become a little more professional in its methods and start using some kind of CAD to develop things. Yep, that's it. Cardboard aided design. Oh, terrible joke. Okay, so I always, rather than trying to write code, I always find it easier to try and have something either physical or an electronic, equivalent electronic circuit in my head, and basically some kind of a picture rather than thinking in code. So we are replacing our little neon and resistor combo here with a new component called it the triplicate, or the triplicator, or something like that. And this is it. This is basically a little Lego cart. The advantages of having grandchildren is with all this Lego and assorted other sort of toys we're knocking around, with a couple of old bolts in to give it a bit of weight, and this is just elastic. And we are going to say the position of my hand here, can we see that? Yep, we can see that. Position of my hand here is the voltage input to our triplicator, and the position of the cart is the current through our triplicator. Now, the way we have it set up here, if I move like that, the little cart moves a proportional amount. So this is basically just a resistor. We've modelled a resistor. Very good. Now let's get our cardboard aided design feature installed, and we'll see what happens then. Okay, so here we now have a little hill made out of cardboard. So if I increase the voltage, the current, according to the position of the cart, is not actually increasing by very much at all until it gets to there, and then suddenly it flips over into this state. And now if I decrease the voltage, there we go, the current drops slowly and then gets to here and then drops off very quickly. So we do have two semi-stable states, and I know this is a real hack, a real bodge up, a real lash up, but you can see that there is also some mass in the cart, including the bolts, so we also have a situation where we have a mass and a spring element, which is the elastic, and I guess some damping, which is in the wheels, the resistance of the wheels. So does that sound like a familiar scenario? Well, if you followed the synthesis tutorial videos, you will recognize that. Okay, so we are going to draw a circuit here. So that's VS and that's GND. This is our capacitor. Remember, this is analogous to our neon circuit, but we are going instead to have our hill component. All that hill. Now obviously this is not any kind of component that actually exists in reality, and I don't think I'd want to try and build one out of electronics. It'd be an interesting project, I guess. However, this is what's gonna happen. So say the current through it depends on the position on the hill, which depends on the voltage across it. It's exactly like the hill, physical hill that we looked at. So when we apply VS, the capacitor will charge up through the resistor, and the current will go up the hill till it gets to there, and the current will shoot up to there, and the capacitor will then discharge through the hill at high current, and the voltage will come down, you see that from my fat finger, until the hill gets to there, until the current gets to there, and it will shoot down to a low value again in the current, and it will start charging up again. So we now need to build this hill in code. Okay, so here is our get hill current function, which actually performs all the functionality of the hill. So hill X is the voltage in, and the return value is the current. So the first thing it does is hill Y is the position of our little car and our little cardboard demo, and it ascertains whether the car hill Y is on the hill or not. Okay, so here we have our hill, and we have our little car. Let's draw our little car on the hill with springs pulling it each way. And we are interested in the force on the car due to the hill. Well, when it's flat there isn't any, so here, here and here there is no force on the car, and this is the force due to gravity acting down. So here this is a half sine wave, so there's no force here, and maximum force here, no force here, no force here, maximum force here. So the force on the car looks like that. 0 for most of it, and then that is half a cosine wave, negative because it's pulling the car backwards, and that's half a cosine wave pulling the car forwards. So let's have a look and see what that looks like in code. So okay, that is the uphill. So it just uses a cosine call to generate that hump, and similarly that's the downhill and the negative sign there, and that's the downhill, the positive sign there. And this is our good old mass on a spring resonant filter, state variable filter, which we've looked at in detail in the synthesizer tutorials. Only here the acceleration is the x, the input, the current position, the y, and because there's a spring down to 0, it takes 2 of those off. That's not that important. Plus our hill out value we've just calculated here, and then minus the damping, and the gain and damping. Hill gain and hill damping are just constant values, preset constant values. And because at this point we're not going into this in any great detail, I'm not going to experiment with those. So then we calculate our mass on a spring velocity from the acceleration and the new value of hill y, the position of our little car, which is simply scaled and returned as the current from our hill component. And if we look up here, okay, we calculate our IR from the Vs minus Vc over the resistor, R charge, this resistor here. We get our I hill from our Vc, and we subtract that from the IR to get the current into the capacitor. The delta V into the capacitor here is just the current into or out of the capacitor over the capacitance value. Again, we're just looking to see what this does. So shall we see what it does do? Okay, what I'm doing here is just driving the input to our hill component with a sine wave voltage and looking at what the current does. And if we look at this, we're pretty happy that's doing what we want, basically. We drive it up the hill here, and then it flips up the hill to here, the top, and back here, flips down again, and the current doesn't really sit in that region at all. So yeah, we can have a look at that in a bit more detail on a spreadsheet. So the yellow trace is the drive, and the green trace is the hill current, and the orange is the hill out. So you can see here it's going up the hill, and the hill is pulling it backwards till it gets to the top of the hill, and then it shoots off again up the hill, and it overshoots a bit, which is an interesting property of the system. And similarly going down again, it behaves in exactly the opposite way, and that is working. So now let's see what it does if we actually connect it to the resistor and capacitor as it's supposed to run. And there it is. So the top trace is the output, so we're getting a nice sawtooth type oscillation, and the bottom trace is the current through the hill component, and you can see it's flipping between a low current and a high current as we would like. And yeah, interestingly, we still see we get that bit of overshoot there, and we can look at it on a spreadsheet. And here it is on a spreadsheet. The yellow trace is the output, VC, and you see we're getting a nice kind of a ramp wave. And the green trace is the current through the capacitor, which we can see is flipping between two levels, and the orange traces the hill out, and interestingly we can see that it's actually continuously going up and down one side of the hill. It goes, the minute it gets to the top of the hill and flips to the other side, it sort of starts coming back again. That's just interesting. Now, next we want to, it being a musical instrument, we want to change the frequency. Now, we will do this here by changing the capacitance value. I mean, I know you can't do that electronically as audio frequencies anyway, but we're modelling, so we can. It's the easiest way of doing it. So let's have a look at the effect that has. Okay, so I've just swept the capacitor value up as the time goes along. Okay, that seems to work alright. But we are driving in our circuit here by setting VS. Now ideally we would want the capacitance value to control the pitch of the note, and we would want that to control the volume, and we certainly wouldn't want it to change the frequency. But let's have a look and see what effect it actually does have. Okay, and here it is. So here we're ramping up the VS value, the drive value, from 0, and there's a helicopter outside, is what the noise is, from 0, well not from 0 here, because it has to get up to the point where it'll pull our little car over the hill before it'll oscillate. So that's what this point is, and once it'll pull it over the hill, then it will start to oscillate. So should we play this? Nothing, 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 and then oh dear, not only does it quite drastically affect the frequency, it does it in a somewhat unpredictable way, in that it goes up and then down. So as I thought, this will not actually do as a sound generation system. It's just been a sort of thought experiment. Can we actually do what we want to do? Okay, so we've actually generated something that oscillates. Well, firstly, a bit of terminology disambiguation, which was confusing me. What we have here, well, we're saying we're going to make a synthesizer without a conventional oscillator, but a conventional oscillator, certainly in a digital synthesizer, is just outputting a predefined waveform. It's not oscillating at all, whereas actually what we're doing here is creating an oscillator, something that does oscillate on its own. So that was something that sort of felt slightly confused to me while I've been making the video, and I've sorted it out in my head now. And anyway, the one we've made is, well, it was just an attempt to get a handle, to make a start on how we're going to work our tone generation system. And it's achieved that. We've got something that makes an audio frequency output with no digital nasties on. So we can now move on to trying to make something that oscillates a bit better and is more frequency stable than that. And we shall look at that maybe next but one time. I think next time we'll jump back on trying to get our musicians' input interface a bit more together. And also, while hunting for other things, found a recorder. I used to be able to play it a bit, but anyway, it's better than that thing. for doing testing and demonstrations and stuff. So that's it for this one. Look out for next one. As I say, further work on the musicians interface, input interface, and the one after that will probably jump back on the sound generation system. So for now, it's goodbye from Triplicate. Goodbye.